Okay, so I think we can start. So it's my great pleasure to welcome everyone to the European Non-Associative Algebra Seminar, and in particular to welcome our speaker Per Bäck from MDU in Sweden, who's going to talk about Hilbert's spaces theorem for non-commutative, non-associative polynomial rings. So go ahead, Per.
Okay, so thank you very much for the introduction and thanks for the opportunity to speak here at the seminar. So Samuel already introduced the topic here, so I will say what this is based on. So this is based on joint work mainly with Masood Aryapoor, who is also here at Mälardalen University. I will mention briefly some results which are joint work with Lundström, Eunert, and Richter, and some which are only results with Richter. All Swedish guys, these mafia. All right, so warning, rings in this talk will be unital. Okay, so Hilbert's basis theorem, the classical one, is like a cornerstone to commutative algebra. Some years after Hilbert introduced this theorem, he started studying twists of polynomial rings. So Hilbert, he wanted to construct an ordered division ring, which was not necessarily commutative. So he took an ordinary Laurent polynomial ring and he introduced some kind of twisting of this. And this gave him an ordered non-commutative division ring. Some years later, Øystein Ore, a Norwegian mathematician, he started studying non-commutative polynomial rings more systematically. So he started this program, really. And these rings, they now bear his name. They're known as Ore extensions. And Noether and Schmeidler, they proved a version of certain special types of Ore extensions already before Ore had introduced them, a version of Hilbert's basis theorem. And then the earliest general version I could find was by Kohn from the 1970s. Some colleagues of mine, they started studying non-associative generalizations of Ore extensions some years ago. And they did this because it turned out that Ore extensions, within the structure of Ore extensions, one can say, there naturally lurks a non-associative structure, which I will tell you about today. Richter and I, we proved versions of the Hilbert's basis theorem for these non-associative Ore extensions. And quite recently, Masood and I, we introduced something we called flipped non-associative Ore extensions. And these are related to the so-called Cayley-Dickson construction. But they're quite similar to non-associative Ore extensions, but they're not the same. So we could also prove versions of Hilbert's basis theorem for these flipped variants. But we sort of got to the question, what sort of underpins this Hilbert's basis theorem? They all seem to be quite similar, the proofs, but we didn't sort of understand, I mean, what is the basic property you need to prove Hilbert's basis theorem? So in these results, it was all described as certain properties of a map. But I mean, what fundamental property is it that underpins it? And at the same time, we were sort of wondering, well, we have all these non-associative versions of Ore extensions. Can we sort of put them under one umbrella? I mean, is there one ring structure to rule them all, and maybe which you can prove this more general version of Hilbert's basis theorem to get at this question? So this is what the talk today will be about. This is the outline, so I will keep it very basic, I think. So I will go through the background quite roughly. So I will first speak about this commutative case, which I think you all know about. And then we will get into this non-commutative case, which maybe not all of you have heard about, and then in the end, we will also get into this non-associative case, which I hope not so many of you have heard about. All right, so let's start off then with the classical case, some warm-up. So a ring is called Noetherian if it satisfies these three equivalent conditions. So the first one is that every ascending chain of ideals should eventually stabilize. I just happen to have this picture from another talk, so it's nice to have pictures in a talk, so I thought I'd share it. So this is what I think about a ring which is not Noetherian. It should look like this, I think. So all these rings, they are ideals. I mean, ideals are also rings, so it sort of makes sense. And if the ring is not Noetherian, you have this infinite chain of ideals. If you have something which is Noetherian, I mean, this chain should eventually stabilize. So you should have something much nicer, at least pictorially. The other condition, which is equivalent to this first one, is that all of these ideals should be finitely generated. So you should be able to find a finite set which generates these ideals. And there should also be a maximal element in every non-empty set of these ideals. Okay, so this is the definition of a Noetherian ring. And Hilbert then proved that if the base ring R is Noetherian, then you can also lift this to the polynomial ring. So this is the classical Hilbert's basis theorem from 1890. Okay, so Hilbert's proof, at least the story goes that it was quite abstract and Hilbert never really produced this basis. It's just proved that it actually exists without showing the basis. So Gordon, who I think was Noether's PhD advisor, he wrote to him that that's not mathematics, it's theology. You sort of have to believe that this basis exists. Right. Okay, so now on to this non-commutative case. So Ore, as I said in the beginning, he was the one who started studying non-commutative polynomial rings more thoroughly. And he was also the one who named them non-commutative polynomial rings. So this is from his seminal Annals paper. So he tried to give the principal results of this general non-commutative polynomial theory. And the guiding principle that he had was that the multiplication should be such that the degree of a product should be equal to the degree of the sums of these factors. Now, generally you don't have this, but at least you have that the degree of a product is at least less than or equal to the sum of the degrees if you work over a general ring with, say, zero divisors, for instance. So, I mean, I thought we could go through Ore's ideas here. So we start with this ordinary ring. So R does not necessarily have to be commutative any longer. And we can view this ring as a left R module. We keep that structure. So we can multiply with elements from the ring from the left. And we want a new product on this ring which satisfies this condition. So what do we need to fulfill this requirement? Well, if we start basic, then for any element R in the ring, the degree of x times R, that should be less than or equal to 1, since x has degree 1 and any element in the base ring has degree 0. So this product as x times R, we should be able to write that as a first degree polynomial, right? And the coefficients of this first degree polynomial should somehow depend on the choice of my R here. That's a natural thing to have. And this actually gives us functions, sigma and delta, on the ring R. I said in the beginning that we're only working over unital rings. So x should be equal to x times 1. And if I now compute x times 1 with this rule I have here, rule number 1, then that should be sigma 1 times x plus this delta 1. And if I now compare coefficients between the left-hand side and the right-hand side, I have a 1 here in front of x, so sigma 1 should be 1, and I have no constant here, so delta 1 should be 0. So that's some kind of requirement for these maps sigma and delta in order for us to then have a unital ring extension. One can ask then, well, what other properties do these sigma and delta need to satisfy in order for us to get a unital ring? So if we compute these two expressions and use distributivity, these things should be equal then. Again, compare, I mean, the top part here with the bottom part, compare the coefficients, and we see that both these maps sigma and delta, they need to be additive in order for us to have distributivity in this ring. So this ring should now also be associative. So we use again this rule, rule number 1, and we compute these two expressions. We compare them, and when we again now compare coefficients, we see that this sigma, it actually has to be an endomorphism, right? And this delta, it has to be something called a sigma derivation. So it's a generalization of a derivation, and in case the sigma is the identity map, then this is really the definition of a derivation. So these are basic requirements of our sigma and delta, and one can now wonder what other requirements are there. I mean, how much do I need to compute in order for me to get a ring? Well, it turns out that this is actually sufficient. So if I give you a ring, an endomorphism sigma, and a sigma derivation delta, then there is a unique polynomial ring which satisfies this rule number 1 here. So if I iterate this rule number 1, I eventually get a formula for how product on monomials work. So this is now the ring product here. So this looks slightly complicated maybe, but these pi maps here that you see, they're just certain sums of compositions of sigmas and delta, which you get from iterating this rule number 1. But at least there is such a formula for computing products. So this will be important for later part of my talk. There is a more abstract definition of an OR extension, which captured the ideas that we started with here. So this is now called a left OR extension. It's because I write the coefficients on the left. So an OR extension now satisfies these axioms. So it should be a ring extension of my base ring. And there should be some element x in this larger ring, which sort of defines my new ring. It should be associative, and it should be a free left-arm module with this basis, just as we have for an ordinary polynomial ring. But the thing that now differs is this last rule. So this is basically rule number 1. When I multiply x with something in R, I should get a first-degree polynomial. And that's it. That's this nice abstract definition of an OR extension. And now it turns out, I mean, not surprisingly, that these rings that we started with, constructed concretely, they are examples of OR extensions. I use then capital X. And also, if you start with this more abstract definition, each of these abstractly defined rings, they will be isomorphic to more concretely constructed one, a generalized polynomial ring, I think I call them. All right, so you have this nice correspondence, I mean, which one definition tells you how to construct these rings. The other definition, this abstract definitions, tells you what these rings are. examples then. So we have this basic rule, rule number one. And well, the first example is just the ordinary polynomial ring. That's the easiest example of an OR extension. So something slightly more difficult then is a differential polynomial ring. So you keep your sigma as the identity map, and you have this delta as a derivation. And then the defining rule is that x times r is equal to rx plus this delta r. And there are many rings that satisfies this rule. The most famous, I think, is the so-called Weyl algebra. So this is the free algebra onto letters x and y over some field k, modulo the commutation relation that x times y is equal to y times x plus 1. And this is simply isomorphic to an iterated OR extension or generalized polynomial ring. And the Weyl algebra started from, I mean, it comes from physics, quantum physics. So x and y played the role of a position and momentum operator. And from this rule, x times y equal to y times x plus 1, you get, for instance, the famous Schrödinger relation, and Schrödinger's cat being dead and alive, and as a consequence of this defining rule in an OR extension. Another example, which connects maybe more to non-associative algebra, is the universal enveloping algebra of let's see, the two-dimensional non-abelian Lie algebra. So there's only one such optisomorphism. And if you write it in the basis xy, it has this defining relation. The Lie bracket satisfies x times y is equal to y. And you can also describe this as an iterated OR extension. There are also other examples of universal enveloping algebras that can be described in this particular way. Okay, I think I have one more concrete example of an OR extension, which I like. So say instead that you take this delta equal to 0 and you let this sigma be some kind of endomorphism. So we'll use this shorthand notation, just x sigma when delta is 0. And now you have this twisting rule that I think Hilbert started with as well, so this Hilbert twist. And the classical example is if you take the complex numbers and you use complex conjugation as a map, that's an automorphism. So you can skew the multiplication in the complex polynomial ring with this complex conjugation. And just as you have that, you can describe the complex numbers as a quotient of a real polynomial ring. You can now also extend this construction to the so-called quaternions. So this is a non-commutative division ring which is four-dimensional over R, and it has this defining relations. You have these three imaginary units which all square to -1. Okay, so Hilbert's basis theorem for these rings then. Well, it turns out that you need the sigma to be an automorphism, and then you can really lift both the property of being right and left Noetherian. So all these examples that I showed you are Noetherian by this theorem. So you start with a field, that's Noetherian. You use the classical Hilbert basis theorem. Then the polynomial ring is Noetherian, and then you use, again, Hilbert basis theorem for OR extensions to conclude that all these rings are Noetherian. All right. The non-associative case then. What about it? So I will start with some basic definitions just to set the notation. So I will denote the associator with parentheses. So this measures the non-associativity of elements. And then the left nuclei will be the set of elements that associate with everything from the left. And similarly, you can define the middle and the right nucleus. In this non-associative setting, I need the definition of a left arm module. So it's this technical definition here. You have an additive group with a biadditive map, and that's it. And since we're using only unital rings, it should also respect the identity element. So this is just the ordinary definition of a left-arm module in the associative setting, only that you throw away the associativity condition. So nothing fancy here. All right. Now, my colleagues, when they looked at order extensions, they started thinking about, well, what if this map sigma and delta do not necessarily satisfy these a bit strange conditions? So sigma has to be now an endomorphism and delta has to be a sigma derivation in order for the ring to be associative, right? That we saw in the previous slide. But if sigma and delta are just additive maps, which satisfies these requirements on the identity element, you still get some kind of non-associative ring structure on this polynomial ring. So the question is, I mean, what kind of ring do you then get? So they started with just the ordinary polynomial ring. So now R is a non-associative ring. And you just look at left polynomials. This is still an additive group. I mean, you just add without any associativity or anything. And then you equip this additive group with a multiplication or a product, which is this Ure type multiplication. So recall here that inside this pi are several sigmas and deltas. But now you don't require that this sigma is an endomorphism and that this delta is a sigma derivation. You just require them to be additive maps, which satisfies this unitality conditions. So that's some kind of non-associative ring. What is it? So recall that we had this abstract definition in the associative setting, which told us what Ure extensions are. So can you still get something in this non-associative, more general setup? And it turns out that you can, so I will call now a non-associative Ure extension a ring which satisfies these axioms. So I've bold-faced everything that has changed from the associative setting. So the only thing that has changed is this associativity condition, which we had in number 2 here. The ring should be associative. If you replace that by X being in the middle and the right nucleus, you get exactly these kinds of rings. And this was sort of set up for these kinds of constructions to correspond to one another. So these more concretely constructed rings with sigma and delta, they correspond precisely to these non-associative Ure extensions, which are described more abstractly. Turns out you can still prove a Hilbert's basis theorem. So recall that this map sigma does not have to be an endomorphism anymore, just an additive map. And if this map is surjective, then you can lift the property of being right Noetherian to the corresponding Ure extension. So in the associative setting, if you consider the map not to be surjective any longer, this theorem fails even in the associative setting. So the smallest requirement you need is for this map to be surjective. So there are counterexamples where you have a right Noetherian ring, but where the Ure extension is no longer Noetherian if the map is not surjective. Okay, now, strangely enough, there is a bijection and a choice of an additive map delta on this ordinary polynomial ring such that this thing is not left Noetherian. So this ky here is of course both left and right Noetherian. So strangely, you cannot lift this property of being left Noetherian even though sigma is a bijection, which sort of was a bit surprising to us that this Noetherian property seemed to have something to do with associativity. You would think maybe that it had to do with commutativity. Left and right would be distinguished by non-commutativity. But here something different happens, which I think I will get back to later. I just want to mention that you can also generalize Ore extension, non-associative Ore extensions in another direction. So you can consider something called abelian groups with operators. So that's a generalization of modules. And you can now consider Ore extensions of these modules and Ore extensions acting on this Ore type of modules. So that's a different kind of generalization, which also generalizes stuff in the associative setting. But I will, in this talk, stick to the ring case. Okay, so the flip map is a map which flips two entries. And I can now flip my multiplication in my generalized polynomial ring. So I will denote a generalized polynomial ring with a flipped multiplication with an FL as an up here. And the product on these kinds of rings are defined like this. So it's the usual product that we had for Ore extensions. But now I sneaked in a tau n here, and this tau n is simply the composition of the multiplication on R and n copies of tau. So really what this gives you is the opposite product in case of n being odd, and the ordinary product if n is even. So I will soon tell you why I'm doing this. But I mean, from a democratic perspective, this is much nicer, I would say, because now both this leftmost monomial has something to do. It's in these pi maps here, it's twisting or skewing the product. And these n maps here in the rightmost polynomial, or these n's in the rightmost monomial, it flips or does not flip the product in case n is even or in case n is odd. So both these monomials have something to do in this product now. So it's more sort of democratic. So an easy example, what kind of ring structure do you get if you now induce this kind of flip? So in the ordinary case, when sigma is the identity map and this delta is the zero map, you get something which is already now very non-associative. So for instance, if I compute this product R times Sx, if I want to move the parentheses and I look at my rule here, it says that, well, x has degree 1, so it has odd degree. So if I want to move the parentheses, I can do that, but then I also need to flip the product here. So you see here that these two expressions are equal if and only if this ring R is commutative. So these flipped polynomial rings, they are associative precisely when the base ring is both commutative and associative. And if you also have a sigma and delta, it gets, I mean, even worse. But let me now explain why I'm doing this. So you can also, I mean, define this slightly more abstract. So here's the abstract definition of these flipped non-associative Ore extensions. So what's changed now is this second non-associativity condition. Now instead you only require that x is power associative. I mean, this means that you can define powers of x non-ambiguously. And instead of this ordinary commutativity relation here, you have three rules. So the first rule here tells you how you can move an x outside an expression like this. And you can do that at the expense of a sigma and a delta. And how can you move parentheses in an expression like this? Well, you can do that, but at the expense of a tau, at the expense of a flip, basically. And the sigma and delta, well, they do not appear here, but they are implicitly Their existence is implicitly implied by this relation x times r is equal to sigma r x plus delta r, as we have in all kinds of OR extensions. Okay, so this is slightly uglier, but it was set up just for these two ring constructions to correspond to one another. So this abstract definitions tells you a bit about what these rings are. Okay, so let me now get to star algebras. So for me, a star algebra is a non-associative K-algebra with an involution, so an anti-automorphism of order 2. And the Cayley-Dickson double of a star algebra gives you a new star algebra twice the dimension as the one you started with. And it has this really strange product, I would say. So it's defined like this, looks completely arbitrary with letters just thrown in. And you can also extend the involution in this particular way to the Cayley double. So even though this algebra seems really strangely defined, it gives you nice algebras, right? So it gives you, for instance, all the real normed division algebras. If you start with star being the identity map and you iterate this process, and you also get their cousins here if you use this mu equal to +1. Okay, but to me this process was really strange. So me and Masood, we tried to understand it better in terms of polynomial rings. So any non-associative star algebra gives rise naturally to a flipped non-associative OR extension. So you use now, instead of this sigma, you use your star. It's an anti-automorphism of order 2. So, I mean, it's certainly additive. And you can also extend the involution to an involution on this FNO. So this is the natural way to do it. It turns out that you can only do it in one more way, and that's if you don't have zero divisor, and then you can also have plus signs here instead. But I will consider this as my natural involution on these FNOs. And now all these Cayley-Dickson algebras, they can be described as quotients of these flipped non-associative OR extensions, which to me and Masood was a nicer description, because polynomial rings we could understand, and quotients of them as well. So, I mean, you can now see the bright side, or if you are inclined to the other version, the dark side of the moon. So, for instance, all these real norm division algebras, they can now be described as quotients of polynomial rings. So to me, this sort of explains what's going on in this Cayley-Dickson construction. So in each step, you add this element x, which squares to -1, and you twist the multiplication with the involution. And the same thing for these split cousins. And I mean, you can also prove properties of the Cayley-Dickson algebras in terms of properties of these flipped non-associative OR extensions. So you can prove, for instance, nuclei, commuters, and center, and so on, and when they're associative, alternative, and so on, in terms of those properties of this big ring here. So that's one way to prove things here. Okay, now my very last part of the talk. So, so far we have sort of constructed our non-associative OR extensions and flipped non-associative OR extensions from, I would say, top down. I mean, what if instead we tried to construct non-associative polynomial rings bottom down? What if we start with like a wish list and say these are the properties that I want my non-associative, non-commutative polynomial ring to have, and then maybe we try to prove Hilbert's basis theorem for them. Then maybe we can sort of get to the point what's Hilbert's basis theorem all about, and what are these polynomial rings all about. So this is Masood's and my wish list of what should a non-commutative non-associative polynomial ring be. So it should still be a ring extension of this basic ring, we think, and there should still be an X. And this X should be power associative so that you can define powers of X. It should still be a free left arm module with this basis so that you can describe polynomials. And the degree of a product should be less than or equal to the sum of the degree. And this can be described as G4 here. So it's completely equivalent to the degree of a product being less than or equal to the degree of the sums. Okay, so this is a wish list. Are there any rings that, satisfy these conditions? Well, certainly there are. But first I should also say that so this abbreviation, generalized non-associative Euler extension, we abbreviate it as a GNOE. And it turns out that it's this creature. So in Dutch, this creature is known as a GNOE. So if you Google GNOE, you will not get generalized non-associative Euler extensions as your first hit, but rather pictures of this animal, which is also called a wild beast, which I thought was nice. Okay, so are there other examples than these creatures of these rings? Well, Euler extensions are exactly the associative GNOEs. So they are precisely the GNOEs that exist in the associative setting. And then if this X lives in the middle and right nucleus, then you are precisely looking at non-associative Euler extensions. So these are two types of rings. So, from this viewpoint, you can also sort of ask, if X is in the middle and right nucleus, what would happen if X was in the left and middle nucleus or in the left and right nucleus? What kind of ring would you get then? And that you can, I think, only say from this bottom-down approach. So I have no answer to this question. So any flipped non-associative Euler extension, that's also an example of a GNOE. Okay, now I want to talk a bit about a Euclidean division algorithm. So a GNOE here satisfies the left Euclidean division algorithm. So these GNOEs were also defined as left GNOEs. And this is maybe a bit technical, but I can sort of maybe give you a flavor what this means. So let's see here. For all elements in this ring and all non-zero Q, if this Q has larger degree than all of these P's, and the leading coefficients of this Q lives in the right arm module generated by the leading coefficients of these P1s to Pn, then I should be able to find some S in the right ideal generated by P1 to Pn. And also this S should be so nice that when I want to compute the degree of it, I can do that in the same way as I can do in the associative setting or in the ordinary setting. So degree of a product should simply be the sum of degrees here. So recall that in this non-associative setting, the ideal generated by this element is a really horrible thing. It consists of lots of parentheses and sums and parentheses again and sums. But if it lives in this degree additive set, you can compute the degree in a nice way. So there is a representation where you can compute the degree as just an ordinary way. And then the degree of Q minus S should be smaller than this degree of Q. Okay, so that's a version of a left Euclidean division algorithm. And now it turns out that if you have a GNOE that satisfies this left Euclidean division algorithm, then you can lift the property of being right Noetherian. So this is, to me, sort of what underlies Hilbert spaces theorem. It's this basic property of having a Euclidean division algorithm. And if you look at OR extensions, non-associative such, the Euclidean division algorithm exists precisely when this map is surjective. So at least to me, that explains why you can prove Hilbert's basis theorem and sigma is surjective. Well, it's because you have this Euclidean division algorithm. And that's really what you use also in the proof of that. Okay, so far I have talked about left OR extensions, left non-associative OR extensions, left everything. But I have not explicitly said so. But there should also be a right version of all the concepts we have looked at. And there certainly is. So if you just look at everything that we did and you use a mirror, then you can mirror the results. So you swap left and right. So if you have a right GNOE, means that you write it should be a free right R module, so you can write the coefficients to the right and so on. And if this GNOE also satisfies the right Euclidean division algorithm, then you can lift the property of being left Noetherian. So, for instance, these rings, they are also right GNOEs precisely when this sigma is bijective. And this sort of tells you when you can also prove the other version of Hilbert's basis theorem. So you start with a left GNOE and you prove that it's right Noetherian, and then you also want to prove that it's left Noetherian. Well, then you try to show that it's also a right GNOE and that you can lift this left Noetherian property. So that's the way to prove this. And in case sigma is an automorphism, then this non-associative OR extension, it also satisfies the right Euclidean division algorithm. So recall that if sigma is a bijection, you can already turn it into a right GNOE. Now there also exists a right Euclidean division algorithm, so you can go back to this theorem here and also prove a left version of Hilbert's basis theorem. So what about these flipped cases? Well, it turns out that they're really flipped. So take a ring which is left but not necessarily right Noetherian. Then you have this infinite chain of right ideals of R, since it's not right Noetherian. And you can also lift this to an infinite chain of left ideals of the ordinary flipped polynomial ring. So these JR they have a really simple construction here, and it's based on the fact that this X flips left from right, so that left ideals become, so that right ideals become left ideals in this flipped setting. And now you have this infinite chain of left ideals, so this ring is not left Noetherian, even though you started with something which was left Noetherian. So this really tells you that the flipped case is really flipped somehow. I think that was actually it. So I just have like one question. I mean, are there other examples of GNOEs? I don't know. So I think the definition is really natural, and I hope that there are some more like natural examples out there. So maybe some of you know about some example that could be described as a left or right GNOE. But that's all for me. So thank you for listening. And here are some references, some recent papers, and yeah, some older papers. Thank you.
Okay, thank you very much. So, does anyone have any questions or comments for Per? Can open your microphones or otherwise write in the chat. Okay, well, I have kind of a general question, which would be the following. I mean, in general, a quotient of a normal associative OR extension will not be an OR extension, but under certain conditions, it is. For your GNOEs, or well, for GNOEs, I guess it'll be harder because they're less
Mm.
axiomatized. But for your flipped OR extensions, do you have sufficient and perhaps also some necessary conditions for a quotient of one of these flipped OR extensions? To still be of the same kind?
No, I mean, really good question, and I haven't even thought about it, to be honest. But I mean, really natural research question, I would say. So,
Okay.
yeah,
Mhm.
probably something to look into.
Okay. Thank you. I don't know if there are other questions or comments for Per. Okay, so if not, let's thank Per back again. And um, we hope to see you all next week. So thank you very much.
Thank you.
Bye bye.
Bye.